left off in the last class. We will just to give you a brief recap of what we were doing in the last class. In the last class we mainly looked at how to develop structural models in Verilog. So, we saw what are the basic gates that are supported by Verilog, and then we saw how we can define structural modules using those gates, how we can use wires to interconnect them, and also stitch together different modules to get larger modules. Now, today what we are going to focus on is the behavioral model. Now, behavioral model is more like a procedure in a programming language. Right? So, it describes the behavior and it still specifies a module in Verilog with inputs and outputs, but inside the module, unlike a structure like gates and wires etc., we can write code to explain what is happening inside that module. So, it is more like specifying an algorithm describing what that module is going to do. And to start with, let us look at go back to the test bench that we designed in the last class. So, we want to figure out how the control flow takes place here. Okay. Now, remember that when we first get into this, the initial block is going to start executing first. Okay. So, whatever is inside the initial block, that is going to be the first thing that we start with. So, we are going to start here. Then after that, we will execute this monitor statement, which is going to set the monitor. Then we will come to this A equal to 0, B equal to 0 statement. Okay. Now, note one thing here is that this is a blocking assignment statement, in the sense that until this is done, the next one will not start. So, there is a implicit control flow here, that after this statement is executed, then this is going to be executed. Now, that is important because you could have written B equal to A here, and then you would actually wanted this 0 to go into A and then that 0 again to come into B. So, if you wrote B equal to A here, it would have the same meaning, but if you put B equal to A here and this is executed before this, then you will have a different result, right. Then we have come across this hash 10. Now, what happens is that whenever the simulation hits a hash delay operator, then it cannot proceed beyond this until all other events, all other assignments that are to be done in the current time are completed. Only then will time increase and then it will go into the next assignment. Okay. So, you might think of this as something which blocks the simulation until other concurrent modules are also ready to jump in time. Okay. Because Verilog is not just one procedure like this, there are several modules which are there, and because this is hardware we are talking about, they are all there in parallel, right. But we have to simulate the thing in a single processor. So, we have to treat them as concurrent, because physically in hardware they are all going to be really parallel, but in simulation we cannot have that. So, we are going to do that serially, but we have to maintain certain guidelines so that the final outcome is consistent with the actual hardware, right. So, here is a summary of the things that we have learned so far, that initial and always begin executing at time 0 in arbitrary order, right. They execute until they come to a hash delay operator. They then suspend, putting themselves in the event list 10 time units in the future for the case at the right. So, here they are going to put B equal to 1 in 10 time units after this, right. So, we are going to study different types of simulator taxonomies and how the simulators work. So, this is purely in terms of an event driven simulator. So, it just schedules the event 10 times units in the future, and at 10 times unit in the future, this is going to start executing once again, right. So, we are going to get more and more into the details of these as we go through more and more of Verilog, and later on when we start studying the way simulators work. So, the question is, if I have two evaluations of two gates G2 and G3 to take place at the same time, do these evaluations take place at the same time? The answer is yes and no. Yes, because they happen at the same simulated time. What do you mean by simulated time? There are two times that we are talking about here. One is the real time of execution, the other time is the time of the simulator. The simulator maintains its time, that is how much time has progressed in the simulation, right. So, when we say that we can simulate 5 millisecond in 1 hour, that means that the circuit's 5 millisecond of simulation takes a simulation time in our computer of 1 hour. Okay, so please understand that there are two times that we are talking about here. So, they happen at the same simulated time because they are two gates which are getting invoked at the same time, right. And no, because we know that the processor is only doing one thing at a given time. So, which is done first? That is undefined. So, if there are two gates which are active at the same time, it can do it in any order. We are talking about structural Verilog once again. You have two gates, both are being sensitized at the same time. They can be picked up for evaluation in any arbitrary order, alright. So, then that you might think that if they have different transport delays, then that can actually propagate to through the circuit in different ways, and it is possible that we evaluate the same gate more than once in the same time, right. So, we are going to see how we can optimize on all that later on. So, the point is that in the real implementation all activity will be concurrent, thus the simulator models the elements of the system as being concurrent in simulated time, even though the simulator executes each element of the design at a time, and we will call it concurrent. Okay. Let us now go into some more of the behavioral Verilog codes. So, this shows a typical structure of a module in behavioral Verilog, where we have this we start with a module name with the port names. We have already seen all these, right. So, we have the input output wire register declaration just like any other things. Then we can have an always block which has a sensitivity list. We have also seen this in I believe in one of the examples. So, whenever this sensitivity list is triggered, then the block that follows it is executed, and that could contain behavioral statements. So, as an example, look at this multiplexer. We had seen a structural implementation of the multiplexer previously. Now, let us see what we have here. We have the output of the multiplexer which is F, okay. This is a 4-bit multiplexer, alright. There is a select line and the two inputs are, both of them are 4-bit. So, we have A and B. Now, when you say always A or B or ACL, it means that when always at A means that whenever A changes, then that is activated. So, when you say A or B or ACL, that means that whenever any of these change, then it is going to get activated, right. So, if A changes, it is going to get activated, if B changes, it is going to get activated, if ACL changes, it is going to get activated. So, typically for combinational logics, whenever any of the inputs change, you would like to evaluate that logic once again. If none of the inputs change, then this sensitization criteria will not hold. So, the simulator will not look inside the module anymore, it will not look inside the always block anymore, okay. So, what do we have inside the always block? It checks if select, then F should be B, otherwise F should be A, okay. So, a simple way of describing what the multiplexer does. Here is another example for designing a flip-flop. Flip-flop has an input D, it has the outputs Q and Q bar. Okay, this is a D flip-flop. So, it has two outputs Q and Q bar. You have a clock and you have a reset. So, in the always block, now see, in the always block we have this begin and end to indicate the beginning and end of the always block. So, always at passage clock or passage reset. What is passage clock? It says that whenever clock rises, positive edge of the clock, whenever the clock rises or whenever reset rises, in any of these two circumstances we are going to examine this. So, when we go inside this, we will check if reset is high. If reset is high, reset is a level sensitive thing. So, whenever it is high, we should assign Q to 1 tick B0. What does this indicate? 1 tick B indicates that this is a single bit and the value of that bit is 0. So, what does it mean? It assigns Q to 0, right, and Q bar is 1 tick B1, which means that we assign 1 to Q bar. So, that is what we want to do when we have reset. Q becomes 0 and Q bar becomes 1. Otherwise at the passage of clock, see, if reset is not high, then it must have been triggered by the passage of clock. So, when we have the passage of the clock, we should record the value of D in the flop, right. So, Q should be equal to D and Q bar should be equal to naught of D, end, right. Is that clear?
So what difference will it make if we write Q is less than equal to 1 B0 and Q bar is less than equal to 1 B1?
Here, see, this one has to be immediate, because the reset takes place even without the I mean, whenever reset is high, you want this to be immediately happening, not in the next clock cycle, not in the next cycle, okay, not at the end of the simulation, it has to happen immediately. That is why it is blocking assignment here, okay. We will see implementations later on where you can wait till the end of the simulation cycle, in which case you will use less than or equal to. Behavioral statements can be of the following types. One is the continuous assignment statement, where we use assign. Continuous assignment means that automatically at all times the assignment is done, right. And procedural assignment statements can be of two types. One is blocking assignment, the other is non-blocking assignment. We will see examples of this shortly. So, what are the block statements? Sequential block statements. A sequential block is a group of statements between a begin and an end. So, whatever you have between the begin and the end, it will sequentially execute all of them one after the other. A sequential block in an always statement executes repeatedly. Whenever the condition associated with the always, see, the always may not be triggered also. You can have always at the rate of something, you can even have always begin something 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 end. That means that it is repeatedly going to be executed, right. If you have always of at of something, then it is going to get executed every time that condition matches. Inside an initial statement, it operates only once and at the beginning of the simulation. You can also have parallel block statements, which can be described by enclosing them within a fork and join. So, whatever statements are there between fork and join, you can think of them as executing in parallel. Okay. This is in behavioral Verilog. So here are 3 examples. Look at the first one. Always at A or B or C, we do this hash 5 D equal to A plus B, hash 10 equal to A minus C, hash 15 F equal to B plus C. Now this block will execute every time A or B or C changes. Okay. This block is an initial block where we have the same 3 statements. This will execute only once at the beginning. This one has put the 3 statements between fork and join. Now note the difference between this and this. Here this assignment, this one takes place in time step in time 5, right. After A or B or C happens, after 5 time units, this one will take place in both of them. What about the second one? When is this going to take place in here? 15, because this is a blocking assignment statement, so control will not progress beyond this until this is complete. So it will wait 5 time units, do this, then wait 10 units and then do this. So total 15. Here this is going to take place at after 10 time units. Why? Because these are 2 parallel ones, right? So that is the difference. Yeah.
What if we put non-blocking statements in the always beginning?
We are coming to non-blocking statements. I will give you examples of that. Now here are comparisons between blocking and non-blocking. Okay. So what are we doing here? Always at A1 or B1 or C1 or M1, we are doing M1 is hash 3 A1 and B1, Y1 is hash 1 M1 or C1. Okay. Now let us look at the times when these are executing. So this assignment will take place at t plus 3. See, the statement is executed at t. Let us say that at time t this is triggered. At that time t, this statement, the evaluation of this statement starts. But remember that it cannot pick up the values of A1 and B1 at that time state, because there is a hash 3 sitting here, right. So M1 to be assigned at time t plus 3. Okay. Then after this is complete, then this statement execution starts at t plus 3 and Y1 is assigned at time t plus 4. Is that clear? Now let us compare that with the non-blocking assignment. In this non-blocking assignment, again the trigger is the same, A2 or B2 or C2 or M2, and then we have put this non-blocking assignment M2 less than equal to hash 3 A2 and B2. So this statement executed at time t, this is also started at time t because this triggers at time t, causing M2 to be assigned at time t plus 3, but there is a difference. We are going to point that out shortly. Now this statement, now since this is non-blocking, so control flow will start moving in spite of the fact that this is not yet completed. Okay. So this one will start at time t also, this one will also start at time t, and it will cause Y2 to be assigned at time t plus 1, because if you start this at time t, then after only one cycle. The other important thing here is that this uses old values. What do we mean by old values? If you used M2 here, I think it should have been M2 here only. This is a typo, this should be M2 or C2. Now if you use M2 here, this M2 will not be the value M2 that this one is assigned. It will use the old value of M2. Okay. On the other hand, here, because this is completed and then you come here, so this value, the new value of M1 will be used here, right. Here the old value of M2 will be used. This should be M2 or C2.
What if hash 4 in the second non-blocking assignment?
In the second non-blocking assignment, if there is a hash 4, then this one will first complete
Yes, sir.
and then it will use that value here.
Isn't it that it's scheduled at a time t only, the Y2 assignment?
It is scheduled at time t, but because of this hash 4, which you are saying that instead of hash 1, if we have hash 4, so it is going to pick up the value of M2 after 4 time units.
But it would have completed the logic N1 or C1 before that also.
No, no, no,
You assign it
no, no, no. This assignment means that you will have to, you cannot progress beyond this hash until your time has progressed, right. So, it is going to pick up these values after that time, alright.
So what difference does the position of this delays make if you put it in front or in
So,
between?
that means that if you put it in the front here, hash 1 y2 less than equal to this thing, then the evaluation of y2 will start after time t plus 1. See, here the evaluation has started here, but the thing that is to be assigned is computed after 1 time unit.
That is if we give hash 4 in front, then it will take the previous values of N1 and not.
If you put hash 4 here,
Yeah.
no, because this one, see, the hash 4 is a blocking statement. It will remain blocked here until 4 time units have passed. By that time M2 will have been assigned, right. So, when it goes past the hash 4, then at that time y2 will be will get the new value of M2. Is it clear? So, that brings us to a very interesting point, that how does what is the sequence in which the simulator is going to do this? What is the scheduling semantics of Verilog? So, think of a set of modules, some having these always blocks, some being in structural, etc. Now, at every point of time, we have certain events which are active. In other words, that those events can be executed now because there is nothing that blocks us from executing them. And there will be some events which are blocked against hash delays, right. So, maybe hash 5 A equal to B. So, that is blocked against the hash 5, alright. And there will be some events which are blocked on at the rate constructs. So, at the rate of A, but A has not changed yet. So, it is waiting. The statements which follow that, they are still not ready to be executed. Now, when you process the current set of statements which are active, that can trigger some of those always constructs. Suppose in your set of active statements there is a change in value of A, then anything which is waiting on always at A will now become active. So, now what we are going to do is we will finish this set of active statements and then look up and see that because of executing these active statements, which of the triggers have become activated. So, if some of the triggers have become activated, then the statements which follow that are going to be brought into the active list, right, and then we will execute them. Again, that in turn can lead to the activation of some of the other constructs. Again, this is going to happen, some new active statements will come on. Remember that in this whole thing, time is not increasing. We are still in the same value of time, right. After this happens several number of times, we will reach a state when there are no active events left and none of the triggers have been activated. Okay. At that point of time, we are what is left? Only those events which are waiting on hash, the delayed events, the events which have been delayed because they are preceded by some hash 5, hash 6, whatever. So out of those, we are going to pick up the one which is the minimum delay, because that's the one which is going to take place. So let us say that minimum one is hash 3. So now we will increment simulation time by 3 and bring that event which follows that hash into the active. Okay, that's clear enough. Now where does the non-blocking business come here? The non-blocking business is different because that when I am processing active events like these, for blocking cases I cannot move into the next procedural statement until I have completed the one. That is the meaning of blocking assignment. So I cannot even reach here until the previous assignment has been completed. Okay? That's not the case with non-blocking. Non-blocking is going to simply put this up as something that we have to do. So it's going to take note that okay, we have started the evaluation of this and we are going to pick up the value of A2 and B2 after 3 units of time and then assign it to M2. Put it aside, okay, and continue the execution of the remaining statements.
So, you said that we will not consider A1 and C1 until there the time has passed. Will we bring A1 and C1 in the active list?
When? In which statement? Here?
No, the previous one, in the blocking one.
In the blocking one?
Yeah.
See, in the blocking one, the simulator is not even going to look beyond this. It is just going to finish this and then go to the next one. It is going to block. The control will get blocked until this is done. Right? In the non-blocking, that's not the case. The control will go through to the next statement. Alright. The non-blocking assignments are very useful for defining finite state machine behavior, where essentially what we mean is that the next state of the finite state machine is determined from the value of the current state and they are all independently determined, right? And so we can assign them using non-blocking assignments so that they are all evaluated, the right hand sides are all evaluated and then they are all assigned to the left hand side. Okay, and is that clear? Okay. So let us look at this this thing, an implementation where we are using blocking assignment statements. So let us see the corresponding implementation as corresponding to this. So here we have this module BA. We have the inputs as clock A, B, output is C, and we are using B and C also as registers. Now there is a mistake here. This B should be an output. Okay, this B here should be an output. Okay, always at passage clock begin B is equal to A, C equal to B. Okay. Now what does this mean? This means that we are going to assign A to B first and then assign C to B. Okay. Now all this is happening in the same clock cycle. So now think of this implementation. This implementation is assigning A to this and assigning A to this, right? Compare this with this one, where we are doing the following thing, that always at passage clock begin B assigned to A, C assigned to B, I mean B assigned to C. Now what this is going to do is, here it is going to use the previous value of B, not the new value of B, right. So the implementation is going to look like this, that whenever you have a passage clock, after the clock this value of A, the value of A that is present here now, will get latched into this, right, into this flop. But the value that is going to get latched into this flop is not that value, it is the previous value of B. So it is this one that is going to get latched here. In the previous case we had actually connected this thing directly here, because it was the same value which was getting latched into both of them. Here this meaning is different. Right? This is a very fundamental difference. Please make sure that you are understanding this thing. Is it clear? There are two types of things that we could use in the behavioral Verilog. One is functions and the other is task. Okay. So a function has a return value, just like our classical definition of functions, and it has a set of arguments. Okay. A task has also a set of arguments, but it does not have a return value. Besides this, they are roughly the same thing. Okay. Let us look at this example of designing a finite state machine using Verilog HDL. So this is a machine which reads input and computes the parity, okay, parity, even or odd parity. So the inputs to this is a clock, a reset, and the input I, which is the bit stream that is coming in, and the output is O. Okay, and the output actually gives whether it is even parity or odd parity. Okay. We are using some registers internally for maintaining the state of the system. We need the state. Why? Because we need to know what is the current parity, and if the current parity is even and you get another one, then the parity becomes odd, and then it remains odd until you get another one. So this is a finite state machine which actually describes the behavior. So when we are in the even parity state, okay, then whenever we get I equal to 1, we go to the odd parity state, and the output is given as 1, and then when we get another one, we go back to the even parity state, and in any of these states, whenever we are there, whenever we get a 0, we just stay in that state, okay, and reset always sends it to the even parity state. We are using two parameters here. What is the use of parameters? Parameters are like variables which you will use in your program, which you will use in your description, but the value that it actually takes can be simply set here, right? Okay. So if you're in here, your definition of the state even is 0 and the definition of state odd is 1. That is the encoding of the state. I could have done the encoding in the other way also, because whatever is your internal state encoding, you can define the output function in such a way that from the outside it looks the same, right? And you are familiar with algorithms which do the state encoding in a way to minimize the number of states and the logic. You have studied that? Yes. Okay. So we are not going into that right now, but what we are going to see is how we use these parameters in our thing. So This one is the part which takes care of the reset. So what it does is, always at passage clock or passage reset, if reset is 1, then the state of the machine becomes ST even, otherwise the state becomes the next ST, and next ST will be defined shortly. So what does this tell you? That when you have reset is high, then regardless of what anything else happens, your next state is always ST even, and ST even is the 0 state. Okay. And whenever the reset is low, then the next state is defined by the next state function. If there is a reset, then the next state function is overridden by the reset. Right? This is one way of defining the state machine. So after this, we are going to look at the state transitions and the output computation.
So why are we given, here only one statement is executed anytime. So why is the need of non-blocking there?
Because we want to take the steady state value of next state. See, remember that there are several concurrent always blocks, right, and they can get executed in any order. I don't want the changed value of next state to be assigned here. I want the stable value of next state from the previous simulation cycle to be assigned here. Are you getting it? See, in the hardware, you are going to have several such concurrent blocks, right? Each of them might be assigning some variables. Now if you have a variable on the right hand side in one of your assignments, then there is a possibility that you may get the old value or the new value, depending on whether that other block executed first or later, right. So that is that's not what we want. In a finite state machine, the machine is going to stabilize to some value, and those are the values which will be used to compute the next state values. We don't use the transient values to compute the next state. We use the steady state values to compute the next state, right. So that is ensured by using the non-blocking assignments here. Is that clear? Now let us look at the state transition function. This is a state transition function where always at a change of the input or in the change of the state, we do the following thing. If I is 1, that means that we have got another 1 in the input. Then if the state is even, we change the state to odd. In other words, we assign the next state to odd, and otherwise the next state is assigned to state even. Now remember that this assignment of the next state will take place in the next clock cycle, in the next passage of the clock, not immediately. See, in a finite state machine, you have received another 1 in this clock cycle. So this next ST tells you which is the next state function, which is the next state, but that next state will become the state of the system at the next passage clock, right. Now see, these are blocking assignment statements, these are not non-blocking, these are blocking assignment statements, but in the previous slide we have these as non-blocking assignment, just to make sure that this assignment of the next state that has changed right now will be used in the next passage clock. This non-blocking assignment will use the previous value. Okay. Otherwise, next state is state. So if the input I is not 1, then we retain the state. So the next state will be the state itself. Now let us look at the output computation. Always at ST, Now we just need to produce the output, change the output whenever the state changes. As long as the state is the same, we do not need to change the output. So always at ST begin, if ST is equal to ST even, then our output is 0, otherwise the output is 1. So in even parity states we output 0, in odd parity states we output 1. Okay. Now note that we define the register O as a register. Why? Because we want O to hold its value through the clock cycle, because there might be some other circuit which will use this value of O. So we need to hold the value of O as steady, right. That is why we define O to be a register and we are just assigning O here. Is that clear? So that is all that we have to do in Verilog. It's a brief overview of the different constructs in Verilog. We are going to look at different problems that come up from the syntax and the interpretation of the semantics of Verilog. One thing that we must be careful about are a set of static problems, like if you see that in the same time cycle, in the same simulation time, a variable is being assigned twice in the same simulation cycle. What do I mean by same simulation cycle? We discussed a little while ago that in the simulation cycle it is going to consider a set of active events, process that, when that becomes empty it is going to look for the events that are triggered by virtue of those assignments. Now the ones that are being triggered by these assignments are validly, they come after the previous set of events, right. So there is no problem there. What I am saying is that if some change here in some variable triggers some other activity, then that activity legitimately comes after this, because that was triggered by this, right. And then again we process those active events, and if they trigger something else, they also legitimately come after that. Though in chronologically in terms of the simulation time they are all in the same time, but there is a temporal relationship between them, that they come one after the other. But suppose in your current set of active events you find that the same variable or the same register is being assigned two different values, then we have a problem, because we have a set of active events. The active events can be processed in any order as per the Verilog semantics. You can process them in any order. So if they lead to conflicting assignment to the variable, then that is what is called a race. It is called a race condition. Okay. And race is something which has to be detected. Race can also potentially lead to problems in the simulation. Why? Because it may so happen that you have continuously a sequence of assignments, a set of active events triggers another set of events, okay. Then when you process that, that again brings some other active events, and this may go round and round in a cycle. If for example you have a combinational loop, if you have a combinational loop in the design, it can happen, it may not stabilize. So you will keep on getting events, simulation time will not progress. How can we detect that kind of a problem? How will what will the simulator do if it sees that for an arbitrary amount of time only this is happening? Right? So these are some of the static checks one has to take care of. Okay. Then after that we come to the actual simulation. How do we process all these events? How does the simulator work? Okay, how can we optimize the simulation time? That is the other thing that we will study. Then we will look at the use of the simulator. See, what is the simulator going to do? It is going to simulate the design by taking inputs from the test module, which are driven by the test bench, right, and then we have to compute the outputs and see whether they match with our expected outputs, right. How do we determine what to test? What should be the test plan? Given a design, what should be the stimulus that the test bench should drive? And how do we determine what part of the functionality has been tested? Okay, that will be the next thing. Okay, after that we are going to go into formal ways of verification. Okay, that is the agenda for the next few classes. Thank you.